Hi everyone! In the last video, we talked about polar coordinates and how they relate to Cartesian coordinates. In this video, we're going to talk about functions in polar coordinates and how to graph them. First, let's talk about the easiest type of functions, the constant functions. If we hold theta constant and let r vary, what we will have traced out is a line through the origin. For example, consider the function theta equals pi over 4. The solutions to this equation are all of the points that can be written r comma pi over 4 for some r. So, we face in the direction pi over 4, and we can walk as far forward or as far backward as we want. You can see that this traces out a line that goes through the origin. It turns out that this line has slope 1, and so this is the equation y equals x in Cartesian coordinates. Next, we hold r constant and let theta vary, and it turns out that we're going to trace a circle. For example, consider the function r equals 5. The solutions to this equation are all points that are 5 units away from the origin, and so we get the circle of radius 5 centered at the origin. Alright, let's get a little bit more complex. Let's look at the function r equals 6 sine of theta. How can we tell what the graph of this function looks like? We could start by just plotting a bunch of points and trying to sketch the graph. It turns out in this case we can actually do a little bit better than that. What we're going to do is try and write this equation in Cartesian coordinates. We start by taking the equation x squared plus y squared equals r squared. Then we can plug in our given function for r and get x squared plus y squared equals 36 sine squared of theta. Now, since a sine of theta shows up, we may guess that this term may relate to y somehow. If we take the equation for y equals r sine of theta, and plug in our function for r, we get that y is equal to 6 sine squared of theta. Multiplying both sides by 6, we find that the right-hand side of the original equation is equal to 6y. And therefore, we have the equation x squared plus y squared equals 6y. To write this in a form we're more familiar with, let's subtract the 6y to the other side, and then complete the square with the y's. And what we're left with is x squared plus y minus 3 squared is equal to 9, which you may recognize is the circle of radius 3 centered at the point 0, 3. From there, graphing functions can get quite a bit more complicated. As a next example, consider the function r equals 1 plus cosine of theta. It turns out it is much harder to convert this equation to Cartesian coordinates. So, the best place to start is probably just plotting a bunch of points. Let's take some nice theta values and plug those into our function. We find that when theta is 0, r is 2, which lands us right here. When theta is pi over 2, r is 1, and so we land right here. When theta is pi, r is 0, and so we land at the origin. And when theta is 3 pi over 2, r is 1, and so we land right here. Connecting all of these points, we get a shape that looks something like this. Since this kind of looks like a heart on its side, we call this graph a cardioid. Let's go ahead and do one more graphing example. Consider the function r equals cosine of 4 theta. Again, we'll start by plotting some points. Because of the 4 theta inside the cosine, we see that the function has a period of pi over 2. And so, we just need to worry about theta values from 0 to pi over 2 to start. When theta equals 0, we get the r equals 1. And when theta equals pi over 8, r equals 0. So, on the interval from theta equals 0 to theta equals pi over 8, r goes from 1 to 0. And so, we get a segment that looks something like this. Notice here that the red dotted lines indicate multiples of pi over 8. Next, when theta equals pi over 4, we get r equals minus 1. Since r is negative, this sends us into the third quadrant, and we get a segment that looks something like this. When theta equals 3 pi over 8, we have r equals 0, and so we return back to the origin. And then, when theta equals pi over 2, r equals 1, and so we finish up right here. And now, since this function has period pi over 2, it just repeats after this. So, to finish off the graph, we can just take this shape and keep rotating it pi over 2 radians until we get back to where we start. The final shape looks something like this, and so we call it an 8-petal rose. The final topic that I want to talk about in this video is how to find tangent lines to polar curves. Suppose we're given a curve written in the form r equals f of theta. We can plug this function into our x and y equations to find that x equals f of theta times cosine of theta, and y equals f of theta times sine of theta. Now, notice that we have arrived at a set of parametric equations for x and y with parameter theta. Therefore, we can use what we know about parametric equations to find that dy dx is equal to dy d theta over dx d theta. Taking these derivatives, we get that dy dx is equal to f prime of theta sine of theta plus f of theta cosine of theta over f prime of theta cosine of theta minus f of theta sine of theta. And now we can use this to compute the slope of polar curves. For example, let's say we wanted to compute the equation of the tangent line to the polar curve r equals theta when theta equals pi over 2. To find the equation of the tangent line, we need a point on the line and the slope of the line. To find a point, we plug in theta equals pi over 2 into our function and get r equals pi over 2 as well. Therefore, the point on the line in polar coordinates is given by pi over 2, pi over 2. Converting this to Cartesian coordinates, we get the point 0, pi over 2. Next, we want to find the slope of the tangent line. To do this, we use the equation we found above. Plugging our function into this equation, we get dy dx equals sine of theta plus theta cosine of theta over cosine of theta minus theta sine of theta. Then we plug in theta equals pi over 2 and get that the slope at this point is equal to minus 2 over pi. Finally, we plug this into point slope form to find that the equation of the tangent line is y minus pi over 2 equals minus 2 over pi times x.